Again, good morning, everyone. I'd like to thank Professor Pollack, not only for his kind invitation for me to present to you today, but also for having the vision to create this wonderful conference all those years ago. And you know, for Annalise and me, this is our third time visiting the conference, and it feels like a family. And you know, with most families, there's some level of dysfunction. But with this family, it's hard to imagine any family that has less dysfunction, actually. So thank you so much, Professor Pollack. So, sound is an aspect of life, but is life an aspect of sound? Well, it's a very interesting question, isn't it? And one that I'd like to explore today. So I'm going to introduce a subject now before we actually get into the main part of this presentation, which again, it concerns water, of course, and it also concerns an aspect of water which you're probably all I know you'll all be very familiar with, and that is the innocent pleasure of throwing a pebble into a pond. When we do this, we see these beautiful concentric ripples that rush away across the pond, taking the information in that little plop sound across to the far edge of the pond or the lake, wherever we happen to be. And but there's all sorts of hydrodynamic aspects to this that we can't see. Before I just go on to those, let's just say, if you have a romantic bone in your body, and you're there at the side of the pond or the lake with your beloved, something really wonderful you can do is to each throw a pebble at approximately the same moment. And when these two little plop sounds occur, you can then stand there holding hands and watching as the energy from one bubble merges with the energy from the other. And you get this beautiful intermixing of the two concentric waves, creating sort of diamond patterns. It's a very romantic thing to do, and Annalise and I often do that. But there's lots of hydrodynamic aspects to this, of course, that we can't see. One of the interesting aspects to it is the speed of propagation. You know, what aspect of physics is causing that particular speed? Well, of course, it's the viscosity of the fluid, in this case, water. But the other thing that happens, and I've shown this in the lab, and we've actually photographed it, is you get a tube torus created in the subsurface of the water. I didn't bring a photograph today to show you, but perhaps I should have done. But you do get a tube torus under the water. And even though classical physics says that water is not easily compressed, in fact, you know, we have the evidence that sound does, in fact, compress water to the extent that the refractive index is changed just a little bit, but enough with powerful lighting to be able to actually see that happen. So tube toruses also happen. But now I want you to imagine these ripples that are rushing away across the water's surface. There's nothing to prevent them rushing away. You know, there's no impedance excepting the general viscosity of the water. But what would happen if there was something that prevented the ripples rushing away across the water? Well, a little while ago, I was contacted by a Japanese friend of mine, Ritsuko Fujimori, and she wanted to have an art project, and she's a photographer. She wanted to have an art project in which she wanted to photograph bubbles in a river. So she asked my advice. What do you think I should do? What camera shutter speed should I use? And these sort of questions. And one of the things I said was, well, if you photograph water, turbulent water, you're almost certainly going to see simulacrums. You know, these are shapes in nature which resemble something else. And so she did this, actually, and she saw all sorts of wonderful things in the water, like angels and birds and butterflies and all these different shapes that, you know, that we imagine when we see these kind of simulacrums in nature. But the other thing that I suggested to her was that if you use a really fast shutter speed, I'm going to predict that you will see Faraday wave patterns in some of the bubbles. You're going to have to be lucky because they only last, theoretically, very short periods of time, a few milliseconds at most. But if you're lucky and you just happen to open the shutter and close the shutter at that right moment, you will see Faraday wave patterns. And she actually did achieve this. And so here are some of the patterns that she saw. Here's one that we kind of call an hourglass, not an hourglass, rather a sundial, beg your pardon. And there are others. Here's another one. Why did these occur? Well, they're occurring because when a little splash of water comes out, say it strikes a rock or something, little splash comes out and plops into the water, that is a sound, of course it's sonic energy, that tries to escape, it tries to propagate away, but it can't because of the turbulence in the water. So that turbulence actually prevents an impedance, a resistance, to the little wavelets that are trying to escape, and they come back and they create Faraday wave patterns. And I believe, if any of you know different, please tell me, but I believe that you're probably the first people ever to see these patterns in water. If you know different, please tell me. I may be a little bit disappointed, but not too much. There's another one there. I don't know how clear they are to see, but... And then there's one more. I love this particular one because it reminds me so much of what Rupert was saying about radiolaria. Can you see this one has a little spike coming out of it? And it's got so much structure in it there. Anyway, I thought you'd find that interesting. And you may be the first people ever to see images, apart from Ritsuko and Annalise and myself. So, moving on. So, bubbles. I'm not showing you any of the angels. That would be for Ritsuko. Actually, I think she's going to publish a book, and I really look forward to that book and seeing all her angels and butterflies. So I'm going to give you a very quick overview. I mentioned this in my presentation last year. Very quick overview. Hydrothermal bubbles, hydrothermal vents, there's not much controversy around the idea, the concept that life emerged around hydrothermal vents. I know some other scientists in history have suggested that they might have emerged in warm little pools and so on, but nevertheless, the mainstream view is hydrothermal vents. And I think for a very good reason, because the conditions are ideal in many ways. First of all, we've got the bubbles, of course, that are coming from the gases that are emerging. And it creates broad sound. Band sound, if you analyze it on an FFT analyzer, you will see it contains thousands of frequencies, audio frequencies, right from very, very low frequencies way up into into low ultrasound levels, frequency ranges. And the wonderful thing about this is that nature has a way of selecting the frequencies depending on the size of the bubble, because each bubble acts as a kind of Helmholtz resonator. It contains a particular volume of gas, and the bubble itself selects its frequency from this melee of sounds that are being created by the vents. The point about this is that when each bubble selects its particular frequency, on the surface of the bubble, there has to be a Faraday wave pattern. There just has to be, because the bubble itself is resonant with that particular frequency, and the surface membrane of that bubble acts as a means of manifesting those frequencies in terms of a Faraday wave pattern. And we have managed to actually image many of these patterns in the lab, and I showed you some of the images in last year's presentation. But one of the things that I think is so important about this particular hypothesis is that when you introduce vibration into a bubble, first thing that happens is a pattern does appear on the surface, but then the bubble also becomes almost lifelike in its behavior. And of course, one of the other things that we know from Professor Pollack's work is that the interior surface of that bubble contains a lot of electricity, so there's an electric aspect to bubbles as well. So let us just start this video and show you what happens. So what I'm going to do is introduce a 21 hertz vibration or sound into this small cuvette. And this cuvette is 2.5 centimeters across. It's square format. Watch what happens when I increase the amplitude level. They start to move around. It's almost as though they're chasing each other around this little cuvette, and I bring the amplitude down, then start to bring it up again, and again, they chase each other around. And you also notice that the tiny little bubbles up here at the top, for example, they're doing nothing. They're ignoring this 21 hertz frequency. Why? Because they're not resonant with it. If I increase the frequency of excitation, then the large bubbles stop moving and the small bubbles start to move around the cuvette instead. A very good demonstration of resonance. But of course, the other interesting thing about this is that this cymatic pattern, or this Faraday wave pattern, that appears on the surface of the bubble. And why is that important in relation to abiogenesis? Well, you know, there are many theories, and I'm going to go through some of them a little bit later in this presentation, but of the many theories concerning how life began, some relating to comets, you know, bringing all sorts of material from outer space into the oceans of Earth, other methods by which these compounds, organic compounds can be formed in the oceans and so on. But overlying all of this is, okay, so we have the building blocks of life in the water. Now, how are they going to suddenly come together to form life? That's a really big question, isn't it? And nobody seems to have a really good answer for it. But one particular idea that may resonate with you is this idea that these Faraday wave patterns on the surface of bubbles represent a model, a way that the building blocks of life can actually come together in a coherent way, in an organized way, and a way to actually form some kind of a pattern of these pre-biotic chemicals. And recently we were honored by a visit from Professor Brian Josephson, and this was the comment that he made. He loved this video, by the way, of the bubbles, and he said that this may help to clarify the way intelligence emerges in nature. A really interesting comment, and because he's particularly interested in intelligent design, which I'll mention a little bit later. And just to mention about the Faraday wave patterns on the surface of bubbles, you see here what I term sonic scaffolding in terms of the modes of bubbles. These are bubble models that are shown from a wonderful book called The Acoustic Bubble. And this shows some of the primary modes of bubbles, but of course, the kind of sounds that I'm talking about are highly complex. They're not necessarily primary modes. They could be really complex modes. And I'd like to show you a quick video now that I think is quite instructive in many ways.
I'm Don Pettit, and we have Dan Burbank here. We're on the International Space Station, and we're doing a demonstration with didgeridoos and oscillation of spheres of water. It's a good thing we have towels set up all around here to catch these flying drops. watch this. Now, I'm going to make these big, and they're not going to spoil off as much water now. That's kind of interesting.
And it's also very interesting to see how the size of the spheres is affected by the tone. So the spheres are tuned, and you can excite a mode in those, and it's dependent upon the tone as well. So it's an interesting mix of science, music, a little bit of culture, and a little bit of cleaning supplies on board space station. So anyways, it's always an interesting exercise to look at all the things around you and try to look at them in a different way.
Very interesting that, isn't it? And notice how, did you notice that the small droplets are not being affected at all by that quite powerful low-frequency sound that he was generating there with a vacuum tube, a vacuum cleaner tube, making it sound like a didgeridoo or yudaki. But the low frequencies are not impacting at all on those little droplets. They're just sitting there, kind of ignoring it. Of course, if you were to measure the energy entering those droplets, you'd find it's exactly the same energy levels entering the large droplets, excepting the small ones are ignoring it and saying, no, we're not resonant with you, you know, so they're just ignoring it. But the large droplets, you notice that pattern that was forming, of course, you can't see the structure in that pattern with that kind of single point lighting that they are using, but in fact, there will be a beautiful pattern forming on that sessile drop. So moving on. So in February 1872, Charles Darwin wrote to the botanist Joseph Hooker, speculating that life evolved in some warm little pond. I mentioned it earlier. Near phosphoric salts, light, heat, and electricity. Of course, there's a lot of controversy these days about evolution. You know, and even Darwin himself knew, and he actually wrote in his wonderful book, that he only had part of the answer, you know, that he didn't have all of the answers. And many people today are suggesting that there was an intelligence in the whole business of creation of life. And this is one of the many books that are talking about this by Stephen Meyer, about intelligent design, and you heard earlier that Brian Josephson is extremely interested in this concept. And I think the reason for it is because when we see the complexities of life, it's so hard to imagine that all of that complexity could have arisen without some kind of an intelligence, right? I think it's a reasonable thought. A theory of intelligent design is not based on religion, but instead it's based on evidence, scientific evidence theory about life origins that challenges strictly materialistic views of evolution. That was by Stephen Meyer. And then what I'm saying is, but what if an organizational force is discovered that can begin to account for the complexity of life, a force that can be viewed to have innate intelligence without the need for intelligent design, right? Interesting idea. Because, you know, if we can identify that force and we can actually see some of the evidence for that force in nature, then perhaps we don't need to look for intelligent design. Now, this, Rupert showed earlier, you know, some radiolaria and diatoms and so on. And I'd like to point out now that all of these different shapes here can be created on the Cymascope. Literally, you just tune in. You have to know which frequencies to tune in. Some of them require more than one frequency, like a high frequency and a low frequency. And when they mix and mingle, you get these various shapes. And you saw, you know, some of that with Lauterwasser's excellent video earlier with the bubble and how it forms into a shape that looks like a living creature. All of those shapes can be created, and a lot more. I showed some of these last year. There's a few more here just to show you. There's a trilobite from 526 million years ago. You know, the image on the left there, the cymatic image or the Faraday Wave image, is so strikingly similar. Here's a starfish, again, strikingly similar. Here's a diatom, strikingly similar. And this, another form of diatom. I mean, in fact, you know, you'd have to be a real expert in this fossilized area to know which is the cymatic pattern and which is the life form. So that's why I put the word cymatic image there, just so that you know for sure which one's which. Here's another one. I mean, look at all these beautiful little antinodes around the periphery, and so on. You know, I could show these all day, but you get the idea that it seems that there is a link between sound and life. One of my scientific heroes is Sir Fred Hoyle, and he, with Dr. Chandra Wickrama Singh, found evidence of prebiotic molecules in spectrographic data from ice clouds in space, and further evidence of carbonaceous chondrites, a species of meteorite. And you probably know that these carbonaceous chondrites, they have so many different prebiotic chemicals on them, and even, you know, you could even say fossilized evidence of life. And there's some conjecture, of course, about that, whether they really are fossilized life forms from space. But certainly there's no question from spectrographic data and from these carbonaceous chondrites that many of the building blocks necessary for life were brought to Earth by meteorites. And there's Sir Fred Hoyle with Dr. Chandra from many years ago, of course. Fred Hoyle is no longer with us, but Dr. Chandra Wickrama Singh is indeed with us. And here he is. And he says, to ignore the evidence for panspermia, which is, you know, the word that he uses, to maintain without any proof whatsoever that planet-bound abiogenesis, whether on Earth or Mars, is the only permissible way to understand the phenomenon of life, is an error that might have adverse implications for the future of science. Because in this field that we're talking about, abiogenesis, there's much conflict about where life emerged. You know, did it emerge first on Earth, or did it emerge in space and was brought to Earth, and so on? Well, some of the evidence now, of course, points to Comet 67P, because this audacious mission of the European Space Agency was so successful. You know, they landed a spacecraft on a comet traveling at thousands of miles an hour, and actually with a mass spectrometer sampled the dust on the surface of the comet. I mean, what an audacious undertaking. But from the data, they saw all of these many different, there's a paper on the subject detailing all of the compounds that were found, the organic compounds, on the surface of a comet traveling through space. I mean, it's extraordinary, isn't it? But anyway, it's true. You know, there's the data. And I'm not going to read all of this, but you know, the key aspect of this is the complexity of cometary nucleus chemistry and the importance of N-containing organics imply that the early solar system chemistry fosters the formation of prebiotic material in noticeable concentrations. Many other wonderful papers on this subject. If this has inspired you to start, you know, looking into this area of science, I can recommend many different papers to you. Here's one of them. One of the reasons I mentioned this particular one is because of the lipids that are sometimes found on these carbonaceous chondrite meteorites. And of course, lipids are a key component of the membranes of cells. There's another one. I love this title of this paper, Origin of Life from Chaos to Orderliness. Because, you know, if anything can create order from chaos, it is sound. And, you know, you saw it in Rupert's wonderful presentation. And I see it virtually every day in the lab working with the Cymascope. So here's a protocell that is showing lipids that are literally surrounding surrounding the cell. And the point about this is that these lipids that may have been brought to Earth by these carbonaceous chondrites can be organized on the surface of a bubble, simply because of sound. So although there are no integral membrane proteins being shown or anything of that nature, we can well imagine that sound has this ability to organize the lipids and indeed to create other forms that can penetrate through those lipids into the interior of the protocell. And we don't necessarily need to believe or to even consider that life emerged spontaneously. It could have evolved over a long period of time. We don't have to imagine that life, in the sense of replicable life, a replication, emerged instantly in any sense. It could have been a protocell that simply lived in the sense of like a virus lives, or some people say that viruses are not alive. Some people say, well, they are kind of, because they exhibit some of the qualities of life. So, I think that it may have been that protocells, these kind of protocells, didn't replicate. They lived, if we can call it life, and then they died, and then more were produced, and more were produced. And then eventually, through eons of time, other mechanisms were brought into this puzzle, again, probably through sound as this primordial organizer. Then, I've called it sonic scaffolding. Amphiphilic molecules may have taken the first stage in the creation of cellular life. The next step needed is a mechanism that can organize formless building blocks into regular morphologies to create orderliness from chaos. Enter sonic scaffolding. Just mentions, obviously, by Stanley Miller and Urey. And going back to what I said earlier, okay, you can, if you put these various chemicals into a flask and you spark them for a couple of days, you will create all sorts of complex organic or semi-organic materials, building blocks, right? So, but were these building blocks, how would these building blocks organized into life? That's the big question. I want to show you something now very, very interesting. It's this here. Robert Brown, the famous botanist, of course, from which we get Brownian motion. We all know what Brownian motion is, right? And it was modeled by Albert Einstein. I want to show you this video of Brownian motion very quickly. This is sent to me by Paul Baker. These are lipids in water, and you see the vibration of the lipids. They're being bombarded. Now, the standard model, of course, of this is that this proved the existence of atoms and molecules and so on, and that these little droplets, in this case, are being moved by simply by the number of impacts, which is, what Einstein predicted. But enter Professor Pollack's wonderful book, The Fourth Phase of Water. There may be another explanation adjunct to this, which is EZ water comes into the equation. And for those of you who have not read the book, probably not many of you here haven't read it, but if you haven't read it, I really recommend you to read it in relation to Brownian motion, because it's a key element in how life began in the primordial oceans. And there's the famous Einstein equations relating to Brownian motion. But there's so much missing from those equations, as Professor Pollack points out. It's not a complete theory. So whatever natural phenomena is eventually discovered to be the true mechanism that underpins Brownian motion, when sound enters water, dynamic Faraday wave results in banishment of the jitterbug chaos, creating exquisite order, certain aspects of which may involve exclusion zones. And here, this beautiful image is simply sound in water, creating that order from Brownian motion, essentially. And here I'm going to show you something really quite extraordinary.
If you ask real experts in probability, they'll say this is not random because it's far too uniform. You know, really, Poisson, that kind of thing would have more gaps and so forth. But it's random enough. And what I'm about to show you works with any sufficiently random dots. Okay. Now, I photocopy this on transparency, the exact copy. I put one on top of the other. The result is this interestingly boring, shall I say, really amazingly boring. But now let's shift the transparency against the bottom sheet a little bit. And what you see is this. You see those concentric circles around a common center. And the reason, actually, in retrospect, is not too surprising because whatever I'm doing to the transparency is a Euclidean motion. And we know that Euclidean motion in 2D is always a rotation. Actually, it could be a translation, but translation is like a rotation with the center at the infinity. So it's always a rotation. So you see those traces of rotation, so to speak, under your eyes. Now, what's happening is that you see the original random dots are displaced slightly, and the images are close enough to the original dots. And when you have a situation like that, human eyes cannot help connecting the dots. You know, those dots are connected, and you see those small segments in your eyes, and then you see those trajectories of the rotation.
So he's saying you can't help but see that, that pattern emerging. He's saying it's an illusion, and indeed, obviously, it is an illusion, but I think there's a more dynamic aspect to it as well. And I just want to show you one last video, which I think will be very instructive.
43.43 hertz image transfer.
So there's 43.43 hertz. We're now going into the low frequency Cymascope. This cuvette's about 50 millimeters in diameter. Gradually increasing the amplitude until we reach the point of Faraday instability. And so we create this beautiful Faraday wave pattern. It's quite difficult to see on this, but first of all, you notice that rotation, and remembering what Professor Tadashi just showed us about rotation. So when there's a slight phase shift, you see this order emerging. And here we have, it's actually the reason for this slight phase shift in terms of the Cymascope is because there's a second frequency being introduced. So we've got the primary frequency, and we have a secondary frequency, just a couple of hertz, that's causing that rotational phase shift. And the other thing that perhaps you can't see so well on that image, on that video there, is the beautiful shimmering effect that you get in the background. And the reason that I think that shimmering effect occurs is because when the sonic energy radiates out, it reaches the boundary where it meets some exclusion zone water, right, at the boundary. Well, it's inevitable that when the reflection of energy goes back to the epicenter, that it carries with it some of that exclusion zone water. And when it does so, we now know that exclusion zone water has a slightly different refractive index to bulk water. And so you can imagine the light coming down from the light ring, striking the water. It's now seeing bulk water, but it's also seeing this slightly different refractive index water. And so this is how you get this beautiful, we think anyway, how you get this beautiful shimmering effect. I had some more slides, but you know, I don't want to break the tradition of me being able to finish my presentation, so we'll leave it at that for the time being. Thank you so much. Thank you.
Thank you very much for this wonderful excursion to the phenomenology of life, because you really shared some aspects, some very important aspects. And before we hop into one or two questions, because we don't have that much time.